look at example 3. Vending machines can be adjusted to reject coins above and below certain weights. This is to help detect for fake coins, but I don't think many people are making fake quarters anymore. It also helps determine coins from other countries or maybe something that might be like an arcade token, just as an FYI. The weights of legal US quarters have a normal distribution with a mean of 5.67 grams and a standard deviation of 0.07 grams. Just in case you ever wanted to know how much a quarter weighed. If a vending machine is adjusted to reject quarters that weigh more than 5.81 grams and less than 5.53 grams, what percentage of legal quarters will be rejected by the machine? Let's draw a normal distribution. My mean is 5.67 grams, and I have to go 1, 2, 3 standard deviations above the mean. So that would give me 5.67 plus 0.07 gives us 5.74, 5.81 when I add 0.07 again, and if I do that a third time, we get 5.88. I have to do the same thing below the mean. So I'm going to subtract 0.07, that gives me 5.60. Subtract again to get 5.53, and subtract one more time to get 5.46. So I was told that my vending machine is going to reject quarters that weigh more than 5.81 grams, so it's going to reject all these quarters, and less than 5.53 grams, so it's going to reject all these quarters. Well, note that 5.53 and 5.81 mark 2 standard deviations. So within 2 standard deviations, using the 68, 95, 99.7 rule, I have 95% of data within those 2 standard deviations. So when I want to know how much is left over, I'm going to take 100%, because remember the entire area under normal curve is 1 or 100% minus the 95%, and that means I have 5% of legal quarters rejected by the machine. I've got 2.5% above 2 standard deviations and 2.5% below 2 standard deviations. Remember, it's symmetrical, and 5 divided by 2 is 2.5. I think vending machines have to be more accurate than this, though, because that means like 1 in 20 quarters would be rejected, which seems like a lot. Let's do one more example. So we can use the 68, 95, 99.7 rule to determine when data values lie 1, 2, or 3 standard deviations from the mean. So let's assume 1,000 students take an exam, and the scores are normally distributed with a mean of 75 and a standard deviation of 7. We want to construct our normal distribution and label our percentages. So let's make it nice and big. We can label our percentages. So I have a mean 75. I go 1, 2, 3 standard deviations above the mean. I go 1, 2, 3 standard deviations below the mean. My standard deviation, sigma, mu for my mean, is 7. So I add 7. 75 plus 7 is 82. 82 plus 7 is 89. 89 plus 7 is 96. I do the same thing below the mean, but now because they are less than the mean, I'm subtracting. 75 minus 7 is 68. 68 minus 7 is 61. And 61 minus 7 is 54. Yes, I did that right, 54. So now I want to label my percentages. So within 1 standard deviation of the mean, we have 68% of data. We'll switch to blue. Oh, we already did blue. We'll switch to green. Within 2 standard deviations, I have 95% of data. And within 3 standard deviations, I have 99.7% of data. So there we have it. Quick question, how much data is left in these little tails Well, we could take 100 minus 99.7 and we get 0.0, we get 0.3% of data. So that means in each tail, we'd have 0.3 divided by 2, which is 0.15. So we have 0.15% of data in each of these tails. So let's talk about how to identify unusual results. These are also called outliers. I forgot a T. Outliers. So in statistics, we often need to distinguish values that are typical or unusual from values that are unusual. Unusual values are values that are more than 2 standard deviations away from the mean. That could be above or below the data. So that would be anything from the outside of 95% of data. So outliers would be this section over here and this section over here, each of which have 2.5% of data because we had 5% left over. We divide it by 2.